Question 7 from Section 2 of the 2019 National 5 SQA exam. A hot water dispenser is used to heat enough water for 1 cup at a time. The rating plate for the hot water dispenser is shown below, and you're given various sort of numbers on it and model numbers. The hot water dispenser takes 26 seconds to heat enough water for 1 cup. And for 2 marks, we're asked to show that the energy supplied to the water dispenser during this time is 91,000 joules. So, in order to work out the energy, we've got to find the power. And remember, the power is measured in watts. So if you look down that list, you can see that we have got the power there below the model number. The model number just is a manufacturer's code. So here we have, down below it, 3.5 kilowatts. So we know that the power is measured in watts. So power equals 3.5 kilowatts. Now remember what a kilowatt is. A kilowatt is 1,000. So we can say that the power is equal to 3.5 times 1,000 watts. And therefore our power is going to be 3,500 watts. So that power rating is 3,500 watts. Now what does that tell you about the energy? Well, we know something else about power. We know that the unit watts, which what power is measured in, I'll put that in a square bracket, is actually equal to joules per second. So it tells you how much energy is transformed or transferred every second. So in order to find the energy, it seems that we'd have to multiply the power by the time. And that's what we do. We take the energy, we want to find the energy supplied, and we take the power and we multiply it by the time, knowing that the units of power is the watt, which is equal to the joule per second. So we multiply by time in seconds, we should get the number of joules. So energy then is equal to the power of the appliance, which we've written out as 3,500. And I'll put in here joules per second just to show you how the units change. Joules per second multiplied by the time, and we're told the time is 26 seconds. You can see the 2 seconds cancel out, and you're left with the joule, which is what we're after. So do that in your calculator. Energy equals 3,500 times 26, and you do get an answer of 91,000 joules of energy. And that's how you do it. So the key thing is to know what power is. It's the rate of change of energy, and energy is equal to power times time. And doing that, you can get your 2 marks. Question 7, part B. The hot water dispenser heats 0.250 kilograms of water for each cup. Part I. Calculate the minimum energy required to heat 0.25 kilograms of water from an initial temperature of 20 degrees Celsius, room temperature, to its boiling point. I'll come back later on in the last part of this question and explain the minimum energy. Well, anyway, we've got 1 kilogram of substance, and we supply a certain amount of joules of energy into that substance, 1 kilogram of it, and it raises the temperature of that substance by 1 degree Celsius. Then we call the amount of energy supplied to that substance the specific heat capacity of the substance. So this is a big clue in what equation to use then. The specific heat capacity is the amount of energy needed to raise 1 kilogram of a substance by 1 degrees Celsius. So if we know how much mass we're heating up, and if we know how much the change in temperature is, we can then work out the energy which was supplied, knowing this specific heat capacity number. And it's usually given in the table here. And since we're dealing with water, you can see that water down there is 4180 joules of energy needed to raise 1 kilogram of water by 1 degrees Celsius. So if we know the mass which we're heating up, and we know the temperature change, then we can work out the energy supplied. And we can get that from the equation which we've always used, and that is EH is going to equal to that number again, C, the specific heat capacity, the amount of energy needed to raise 1 kilogram of a substance by 1 degree Celsius. So if we're raising up m kilograms of it, we have to multiply by m. And if we're raising it beyond 1 degree Celsius to a certain change in temperature, we'll call delta T, then we have to multiply by that change in temperature, delta T. And that's where we get that equation from. So all we have to do is plug in the numbers. the specific heat capacity for water, we look at the table again, we've highlighted it there, and it's 4180. We know the mass of water we are heating up at 0.250 kilograms, and this change in temperature, we're going from 20 degrees Celsius right the way up to 100 degrees Celsius, so our change in temperature is going to be 80, and that's our change in temperature, 80. And therefore, we do that in our calculator, we can find the energy needed to do this, the minimum energy we need to do this, and it's going to be 83,000, if we work it out, 600 joules. Now, why am I saying minimum energy? Because obviously when we heat something up, not all the energy is going to go into the substance, it's maybe going to escape into the air or the surrounding area, so we have to quote that value being the minimum energy needed to do that. We have to put in more energy in order to cover the losses, which would take us below 83,600 joules. Question B, part 2. As the water is dispensed into the cup, steam is released. And for 4 marks, we're asked to determine the maximum mass of steam that can be produced while the water for 1 cup is being heated. Now, we're playing for 4 marks, which means there's a wee bit of physics involved in here. So let's go back to the beginning of the story and review what has happened. The heater has supplied a total energy input of 91,000 joules. We did that in the first part of this problem. Now, the temperature of the water has gone up from 20 degrees Celsius to 100 degrees Celsius boiling point, and we worked out that the minimum energy needed to do that was 83,600 joules. So that's the cost of raising water from 20 degrees Celsius up into boiling point. Now, as you can see, there's a shortfall in energy. Where's that shortfall of energy gone to? It seems to be hidden somewhere. And that gives you a clue, because what has happened is when you raise water from 20 degrees Celsius to its boiling point, and when it's sitting at its boiling point, 100 degrees Celsius, any more energy you put into the water does not raise its temperature, but what it does is it changes some of the water into steam. And the amount of excess energy you put in above the boiling point of water, when it's sitting at boiling point of water, that will be this energy here. So this is the energy used to vaporize a mass of water at 100 degrees Celsius. And we can work out what that energy is. The energy required to do that is, well, we put in 90,000, so 91,000 joules were put in originally. If we take away the 83,600 joules, we are left with the amount of energy which is going to be responsible for changing the state of water, liquid water, into a gas, and that gives us a clue as well. So we do that calculation, we end up finding out we have 7,400 joules that's gone into the water to change it into the gas. Now, the key equation for this one is the following. It is EH, that's the energy put in, which will change a certain amount of water, and the key number here is this number called L, which is the vaporization. L is called the specific latent heat of vaporization, which we can bring in here like that. Now you can see that for water it's going to take 22.6 times 10 to the 5 joules of energy to change 1 kilogram water into 1 kilogram of steam. So we know we have put in 7,400 joules of energy above the boiling point, so therefore we can calculate, if we know the specific latent heat of vaporization of water, which we do, it's marked there, we can work out the mass of water which has been changed into steam. So we just do a wee bit of rearranging here, and we have EH, which is what we just worked out there, 7,400, divided by the specific latent heat of vaporization of water, and that's going to give us the mass of basically of the steam. So put in the numbers, 7,400 joules divided by, and it's a very big number here, 22.6 times 10 to the power 5, and it's going to be joules per kilogram. So we do that in a calculator, we end up with a number according to our standard, our scientific notation, 3.3 times 10 to the minus 3 kilograms. So we change that into grams. We know that multiplying a kilogram by 1,000 will give us grams. So if we multiply 3.3 times 10 to the minus 3 kilograms, we get 3.3 grams of steam. So that's what we've got produced there. So just to recap that again, we have put in a total energy of 91,000 joules into that water. 83,600 joules has been used to raise the water from 20 degrees Celsius up to its boiling point. Any additional energy added into the water will not raise its temperature, but will change the water into what we call a gas, and it's called the vaporization of water. Now the key number here is the specific latent heat of vaporization of materials, and for water it's 22.6 times 10 to the power 5 joules per kilogram. What does that mean? It means if you want to vaporize 1 kilogram of water into 1 kilogram of steam, you need to put in 22.6 times 10 to the power 5 joules of energy. Now we know we've put in that amount. That's the excess energy for this part here. We know that's the excess energy. Therefore, by using EH equals M times the specific latent heat of vaporization, we can rearrange, plug in the numbers, and we end up with 3.3 grams of steam produced. Question 7, Part B, Part 3. Explain why, in practice, the mass of steam produced is less than calculated in B2, the previous question. Well, let's take a look at what we did in the previous question. We put in a total energy into the water of 91,000 joules of energy. We needed 83,600 joules of that energy to raise the temperature of the water from 20 degrees Celsius up to boiling point. And once the water was at boiling point, any excess energy which we put into the water, represented by this little block here, was used to change the water into the gas, and the height of this represents the amount of excess energy. So obviously the bigger this block is, the more mass is produced. Now let's take a look at this situation here. We've got the same energy inputs, but this time some of the energy is going to be lost to the surrounding atmosphere. Some of the energy is going to be used up heating up the cup. Some of the energy is going to be used up actually being lost in the actual appliance itself, heating the different components of it. So that big chunk of 91,000 joules of energy, you're going to lose some, and it's going to disappear. And once it's disappeared, you can see what's going to happen here. You can see we've got less energy now to change some of the water into the gas. We can compare it. And you can see we're going to make less mass of steam because we've got less energy above the 100 degrees Celsius boiling point. So the answer to this question is quite simple. We actually produce less mass of steam because the total energy input is going to be less, because some of the energy is going to be lost to the surroundings. And once that energy is lost to the surroundings, it gives us less energy to play with once we have spent energy getting the water up to boiling point. That's the amount of energy we've got left, which is shaking there, which is not as big as the original amount of energy, because we've lost energy from the total energy input, the result of which we're going to have less mass of steam produced.